everyone. My name is Kurnia Ramadanti Dohaza. My NPM is 233128183 from class EF 23A. This I want to explain about the basic concept algorithm. Number 1. The basic concept of an algorithm. An algorithm is a precise step-by-step procedure designed to perform a specific task or solve a problem. It takes an initial input, process through a series of well-defined instructions, and produce an output. Algorithms are central to computer science as they guide how tasks are automated and how problems are solved efficiently. For instance, if we need to sort a list of numbers, an algorithm provided a systematic way to perform these tasks. Some key properties of algorithm include A. Correctness. The algorithm should solve the problem for a valid inputs. B. Efficiency. It should use resources like time and space efficiency. Definiteness. Every step of the algorithm must be precisely defined. Finiteness. It should terminate after a finite number of steps. E. Inputs or output. An algorithm takes input data and produces an output after processing the input. Number 2. The theory of algorithm complexity. Algorithm complexity is a field of study that focuses on the performance of algorithms in terms of the resource they consume. The most common resource considered is time or execution time, but memory or space complexity, and even other resources like bandwidth or energy can also be considered. Categories. Number 1. Time complexity. Time complexity measures how the execution time of an algorithm increases as the size of the input grows. It is important because an efficient algorithm saves computational time and allows for the handling of larger inputs. Number 2. Space complexity. This measures the amount of memory the algorithm uses relative to the input size. An algorithm that requires a lot of memory may be impractical for large inputs even if it turns quickly. Primary goals. The primary goals of complexity theory is categorize algorithm into efficiency classes. This is where big O narration comes in, which describes the worst case scenario of how the algorithm runtime or memory usage grows as the input size increases. For example, consider a linear search algorithm, or where you go through a list one element of a time. Its time complexity is O n, meaning the execution time grows linearly with the size of the input. On the other hand, binary search, which eliminates half of the remaining elements with its comparison, has a time complexity of O log n, which is more efficient for a large input. 3. Types of asymptotic time complexity. Asymptotic time complexity helps to understand how an algorithm running time happens as the size of the input becomes very large or approaching infinity. This allows us to classify algorithms into broad categories based on their efficiency. Here are the most common types. A. Constant time O1. The algorithm's running time does not depend on the size of the input. No matter how large the input is, the execution time remains constant. Example: accessing an element in array array using its index. B. Logarithmic time O log n. The algorithm reduces the problem size with each step, often by half. As the input size increases, the number of steps increases logarithmically. An example is binary search. C. Linear time O n. The running time increases proportionally with the size of the input. If the input size doubles, the execution time also doubles. Example: iterating through all elements of a list or linear search. D. Linearithmic time O n log n. A combination of linear and logarithmic time complexities, often seen in more efficient sorting algorithms. Example is merge sort and heap sort. Next, E. Quadratic time O n quadrat. The running time increases quadratically with the input size. Algorithms with this complexity often involve nested loops. Example: bubble sort and insertion sort. F. Cubic time on O n cubic. The running time increases with the cube of the input size. This is seen in algorithms that have three nested loops. Example: symmetric multiplication algorithm. G. Exponential time O 2 expon n. The running time doubles with each additional unit increases in input size. Algorithms with this time complexity are highly inefficient for large input. An example: solving the Towers of Hanoi problem. Brute force algorithm for combinatorial problems. H. Factorial time O n factorial. The running times grow factorially with the input size. This is usually seen in brute force solution to complex problems, such as solving the traveling salesman problem by trying possible routes. The last but not least, types of algorithm based on Big O notation. Algorithms are classified based on their performance using Big O notation. Some common types include: A. O log n algorithms or logarithmic time. These algorithms, like binary search, reduce the problem size by a factor, usually helping in each step. This is much faster for large datasets compared to linear time algorithms. B. O n algorithms or linear time. These algorithms scale directly with the size of the input. A common example is linear search, where you traverse through a list of or array element by element. Next, O n log n algorithms or linear arithmetic time. Algorithms such as merge sort or quick sort in a parent case are examples of linear arithmetic time complexity. These are highly efficient for sorting large data sets as they combine logarithm reduction in problem size with linear steps to solve the smaller subproblems. D. O. N quadrat algorithms or quadratic time. Many simple sorting algorithms such as bubble sort, selection sort, and insertion sort fall into this category. This algorithm typically use nested loops to solve the problem, making them inefficient for large inputs. E. O. N cubic algorithm or cubic time algorithm like some matrix multiplication techniques that involve three nested loops often fall into this category. Although less common than O and cubic algorithms, they are still inefficient for large input size. F. O. 2 exponential and algorithms or exponential times. Exponential time algorithms like the brute force solution to the Towers of Hanoi or certain dynamic programming algorithms quickly become infeasible as the input size grows due to their steep time growth. G. O n factorial or factorial time. Algorithm with factorial time complexity such as the brute force solution to the traveling salesman problem are extremely inefficient for large input. This algorithm involves trying all possible permutations of a set of elements, making them impractical for all the small instance. That's all from me. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.